So, last 2 days we have discussed about the basics of measurement systems and particularly the linearity, different definitions, and also uh, the calibration and etc. So, you will be mostly doing the tutorial problem 1, which we had already circulated. And for the first day, I will try to solve some of the problems or rather the how to approach and like this. But before doing that one, I would like to talk about one more thing which you are probably familiar. In the measurement class, you must have heard the loading effect. The loading effect you must have seen or like this, that if we want to, the basic thing was that if we want to measure in a nutshell, we can say, if we want to measure the voltage from of a source or from across 2 points, the meter resistance must be very high compared to the source resistance part, because the very basic thing is that it should not, the measuring, once you connect the measuring system, it should not affect or load or change the performance of the actual system for which we are measuring. It is obvious and all things there. So suppose some a some beam is vibrating. Some beam is vibrating, and to measure the vibration, I put a vibration detector there. But the vibration detector must be very small in mass, because if the mass is large, it will definitely load that one, and as a result, the vibration frequency will change. So naturally, these are the important things that any measurement systems, if we want to measure, we should be careful that it does not load it in that one. But here I would like to, uh, so naturally the measurement loading effect will cause you the error in measurement, but also what we can say also, the loading effect increases nonlinearity. Sometimes it is the loading effect increases nonlinearity. So, how it is and why it is, let us try to see that one. We just take a same example or the very simple example of a potentiometer. We call it E, and this is a long potentiometer. Maybe total resistance is RT, and this is a wiper. The distance, total distance, say suppose a linear potentiometer we call it. The distance traveled is, say suppose, xi, and the resistance is Ri, and here the total distance is xt, total distance. So we know that ideally the output voltage E0, if we measure it, it is E0 is equal to Ri by Rt into capital E, or we can say it is Xi by Xt into capital E. So it is totally linear. But if we connect a meter, and suppose this we connect a meter, and suppose the meter resistance is Rm, any meter. Meter resistance is Rm there. And we are assuming right now, obviously, this our case is that if Rm is infinitely large, it is not going to affect. But if Rm is not that large, so it is comparable with the potentiometer resistance, then what will happen there? So if we look at it in that case, if we try to find out what is the value of E0, what we can say is that it is we can draw the Thevenin's equivalent circuit. This is ETH is the Thevenin's equivalent voltage, RTH is the Thevenin's equivalent resistance, and the meter resistance is Rm. So ETH is nothing but the ideal voltage. So here it is Xi divided by Xt into T there. Okay. So what is the value of RTH? It is basically Ri parallel with Rm, Ri parallel with Rm divided by Ri parallel with Rm plus of RT minus Ri. Can I write it? Is it okay? Because, no, here it would be into RT minus Ri. This two, no. RTH is this, sorry, parallel to this one. Sorry. So I would say that here it is total resistance is Rm parallel with Ri. That means these two resistances, and then, oh sorry, this I have removed it. Oh, that's what I am missing. This is basically RT minus, please excuse me. That is, if once I remove it, here it is Ri parallel with RT minus Ri. So here it is Ri into RT minus Ri divided by RT. Am I correct? Please correct me if I am wrong. So what it would be, E0 is equal to Xi. Okay. This one, RTH, we can also write it down is equal to Ri divided by RT into RT into 1 minus Ri by RT. So here it is Xi by Xt into RT into 1 minus Xi by Xt. Okay. So what is E0? E0 is equal to ETH, sorry, E0 is equal to RTH divided by, sorry, Rm divided by RTH plus of Rm into ETH. Okay. So what I will say? That this is equal to, what is RTH? It is Rm divided by Xi by Xt into RT. You may think that we are going unnecessarily complicating it, but possibly after some time we will understand why we are doing it. Plus, but please correct me if I am doing some mistake there. So here it is Xi divided by Xt into E. Is it all right? So I can simplify that E0 divided by capital E is equal to Rm divided by, what is it? Rm, I am just putting Xi by Xt, all of them together. So it is Rm into Xt by Xi plus of, what is it? This Xi by Xt has gone. So it is RT into 1 minus Xi divided by Xt. Okay? And this can be further written that it is equal to 1 divided by Xt by Xi plus of RT by Rm into 1 minus Xi divided by Xt. Is it okay? I think this relationship looks to be okay. So now the question is that if the meter is very high resistance, so if your Rm is tending to infinity, so what will happen? If Rm is almost looking to be infinity, I hope this relationship is okay for you. Please check it. But this, if Rm is going to be infinity, so what will happen? I make the characteristics Xi by Xt, and here E0 divided by capital E. Here it is Rm is approximately, say I call it infinity, very high, or rather RT by Rm is equal to 0 or like this. So it is your ideal condition. If we look at it, if it is 0, it is Xi by Xt, and it would be a straight line like this. And this case, it is also 1.0. So if we know that if Xi is equal to 1, Xi is equal to Xt, the output voltage will also be E0 E0 will be is equal to capital. So these points and these points are always fixed. But the point, what will happen if Rm now decreases? So what will happen? If Rm decreases, then the question will come, or rather I will put it, if you don't mind, I will put it, it is RT by Rm equal to 0. So if I put it RT by Rm is not equal to 0, that means this part is introducing nonlinearity in it. So what will happen is that these characteristics will go like this. So here it is increasing RT by Rm. So as the potentiometer resistance increases and comes to be comparable with the meter resistance, it is causing the loading effect, and the loading effect will be causing what we say the nonlinearity. The potentiometer characteristics is no longer a non-linear one as we had thought of it because of our improper selection of RM. I leave it to you to show that. So, show that maximum error due to a nonlinearity, this occurs when xi by xt is approximately, you can see the error is increasing, and it is approximately at this point the error is maximum, like this. Okay. Up to this we have we are confining ourselves towards the loading effect, and we have seen that this is a potentiometer example. Obviously here it's a crude example where we are not using a meter which is a digital multimeter which is have a very high resistance and like this input resistance or not, but if it is there, but this will be causing the nonlinearity due to the loading effect of it. Now the question is that what is the remedy? Because this is already not, I mean, say suppose we have that RM is not, we don't have any other meter which has, and the meter resistance is low and comparable to this one. Can we decrease the nonlinearity? What is the way we can decrease the nonlinearity? So I just put it, what is our remedy? Okay, we can think of several ways or like this there. But one way I just give you the answer. You please try to think of. Okay, let it be there, but I have added an extra resistance across these 2 points there. And across the extra resistance across these 2 points, and let this resistance value be equal to Rm. Let this resistance value be Rm. Then looking at it without going to the detailed calculation, can you tell me what would be the characteristics? Definitely this is our ideal characteristics. But what is the actual characteristics? What is the change in the characteristics due to the introduction of the extra resistance Rm? Anybody, can you tell me? Without calculation, without, just for our, simply from common sense. I look at it in this way. Okay, definitely whenever xi equal to 0, the output voltage is 0. When xi is equal to xt, the output voltage would also be capital E. These 2 points are already fixed as it was in the earlier case. But in between, what is the change? Now can you think of what will happen if this xi by xt is equal to 0.5? What will happen? If it is 0.5, this is coming Rm, this is coming Rm, this is at the midpoint, RT by 2, RT by 2, parallel Rm, and here RT by 2, parallel Rm. Perfectly symmetrical circuit. So what will be the value? This value will be simply half of, this will be simply 0.5. This will also be 0.5. So you can now relate what we had studied in the last class, which is equivalent to your, what we said is that 3-point calibration. If you recall, if you go to your notes, it is a 3-point calibration. That means we have fixed these 3 points and it cannot move it. And naturally, what will happen is that we will get a characteristics which is much closer to these characteristics, closer to the ideal one compared to the extra resistance added to it. So what we can say is that what we are achieving is similar to your 3-point calibration here. And from there, what we can say, we can achieve very closely, I mean rather better characteristics, more linear characteristics or like this. And I leave it to you to deduce that in this case the relationship is E0 by E is equal to 1 minus x plus q divided by 2 into 1 minus x plus of q divided by x, where q is equal to Rm parallel RT and x is equal to xi divided by xt. So if we plot it, we will see it that they are satisfying. But the interesting thing is that just putting a resistance, even though the Rm meter is not that good enough meter, I can compensate the a loss of accuracy or loss of linearity to some extent there. So from this one, I can conclude also that often the instrument, the sensor or the measuring system, even if it is accurate, but by inappropriate choice of the meters and all the things there, it sometimes causes this sort of problem, which is a which will deteriorate the performance. And the second point is also there that by making some trick like this selection of R1, putting an R1 here, there, we can overcome many of the difficulties and simplify many of the problems there. So it is always try to identify what is the problem and try to sort it out what is the area. What is the simplest way we can solve it and at that point and simplify in a simplified manner there. So you must be thinking that why it is in tutorial class. I have been talking all the things there. But if we recall, if you go through your tutorial sheet, we will find a problem that is problem 7 of your tutorial sheet. Okay, there was some resistance, you can forget it, but anyway, I am just putting it. So, what is the A there? It is the point is xi by xt. I am just telling that we try to find out the case of 0.5 there. Okay, 0.5 there. So it appears that okay, we are doing the same case like this. There, we are measuring. I mean, very innocently, if we like it, to it, we are measuring a voltage across the potentiometer and amplify it by an amplifier. But what is happening? What is the input if I consider it? This is your load or the meter or like this. What is the input impedance of this meter or this system, the measurement system? What is the input impedance? You must be knowing that one, that this is because this point is virtual ground. The input impedance is approximately it is 100 kilo ohm. So, what we can, and for incidentally, this input impedance of this one, this circuit, and the meter resist, I mean the total potentiometer resistance are almost the same there. So, what will happen? Will it, so what will be the effect? This amplifier, use of a inverting amplifier, what is it causing? It is causing that loading of the potentiometer, because some current will be flowing, this will be drawing some current from the potentiometer, or rather say this will be loading the potentiometer. And naturally what will happen is that it will be the same case as we have done it earlier, considered earlier without Rm. That is the thing there. That Rm is nothing but this 100K there. So, what will be our A equivalent circuit? It would be, if it is so, if I say this is your small e, what is the value of small e in this case? This small e would be this 100 parallel to 50 ohm or like this. So, here it is if T parallel 100K and this is your voltage E0. So here it comes to be, please check it. Here it is E0 is equal to 33.3 divided by 83.3 volt into 1. So here it is coming to be 0.4 volt. So what we can say in this case also, ideally if it is at the midpoint, I should get a zero point 0.5 volt, but the deviation from the linearity is as much as 1.1 volt. And if I look at it, so it is E, okay, I call it E, and if it is E0, is the output voltage is equal to minus 0.8 volt, because the gain is 2 there. So ideally I should have minus 1 point volt for the midpoint potentiometer. But now you are seeing 0.8 volt minus 0.8 volt of this one. And naturally what is happening is that it will give you a wrong reading and wrong conclusion. If suppose I am measuring some displacement using this potentiometer, because it is not the problem of the potentiometer, but due to the inappropriate choice of the measurement system, what is happening, that there would be an error, considerable amount of error in measurement, almost 20% error in measurement, because of the inappropriate choice of the measurement system there. So what is the remedy? Anybody, can you tell me, suggest me what is the way out? If I want to measure accurately that there should not be these errors due to this loading effect. Anybody? Anyone can suggest? Aditya Basu, what is your
So
opinion?
we'll add 100 kilo ohm resistance in
Where?
there. Like,
Where?
so the where you earlier in the previous circuit you suggested. Like,
Okay. Here.
yeah.
That is A there. But can we not design a different type of circuit? That is definitely one more way, but it is not reducing, completely eliminating the nonlinearity, maybe reducing it. And again, extra resistance you are putting it. Any other way for the designing, at the stage of designing of the amplifier? Anybody else, can you suggest?
So we can use a buffer and then we can amplify it.
Yeah. Basically, what is buffer?
A non-inverting amplifier.
One,
Non-inverting.
non-inverting. So we need not use a non buffer. Actually, it is a non-inverting amplifier. If I had chosen, instead of this inverting amplifier, if I had chosen, say here it is 1K, or rather, okay, I put it all 100K. What is the gain? The gain would be 1 plus Rf by Ri, 1 is equal to the 2, the same gain. But what is the advantage? The advantage is that this is an ideal op amp, even though we consider it non-ideal, but the point is that there is almost no current flowing through this one circuit there, because it has got an infinite input impedance there. So naturally, this, if I had connected this potentiometer with this one, instead of the circuit I have shown it earlier, I could have nicely got a very linear characteristics. I got a nicely a very linear characteristics here. So wanted to, but the same because there is we are elimination. So here it is no loading effect. We could get it like this. So definitely when we want to design a circuit, we must see whether the circuit is compatible with the sensor or signal conditioning circuit is compatible with the sensor. Otherwise, a wrong choice may lead you a lot of to a lot of error there. Okay. So that is basically why I told all the things was only to solve the problem 7. But the problem 7 just not only a problem, but it explains many of the very basic things there. Similarly, I would take up one more problem, that is problem 1. Please participate. If you have any question or any doubt or anything, suggestions, you please come to them. So problem 1A. Okay. It has got a, I think these things we have must have been discussed while discussing the Wheatstone's bridge. So Wheatstone bridge, mostly we talked about initially the balanced bridge, but in the measurement systems of the instrumentation, we often use an unbalanced Wheatstone bridge. That means maybe a resistive sensor, maybe as I told, resistive sensor, maybe some uh, 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 similar to your potentiometer for distance measurement, or maybe uh, a resistance thermometer, which resistance changes linearly with the input x there. So here also, if we solve it, it is like this: E0 is equal to E into what we can say it is R into 1 plus x divided by R into 1 plus x plus of R minus of R divided by 2R. So we have it E is equal to E into R. I can put it all 2 plus x and here it is 1 plus x minus half. So I can put it is equal to E into 2 plus x into 2, and here it is 2 plus 2x minus 2 minus x, like this. So it is coming to be E into x divided by 2 into x plus 2. Okay. In fact, the maximum sensitivity, it can also be shown that the maximum sensitivity can be achieved in this case where the bridge arm ratio is 1. But I am not concerned about this one right now. But if I plot E0 by E versus X, this is your ideal case, which can be ideally E0 is equal to Ex by 4 if x is far less than 2. Very small, so suppose 0.1 and like this, it will have achieve a linear characteristics. Okay. So here it is that value, I am not putting it like this, but as x changes, say from 10% it goes to 20%, 30% or like this, what will happen? You can see as x increases, the denominator part increasing, naturally there would be more deviation from the linear scale. So what will happen is that for this is x is, say suppose this is x1, this is x2, and this is definitely which is greater than x1. So what we can say is that in this case, more the value of x, more will be the deviation from the linear characteristics. But even for the small values, we can, for say x is equal to 0.1 on 0.2, you will get a very linear values there. I think this characteristic should have been here. Now the point here again, the linearity is important. So naturally, this is the thing, deviation from linearity is causing a big concern there. So many of the cases we may cause have trouble for this one. So we look for another configuration where it is the bridge arm ratio is equal to, which is actually the problem 3. No, not problem 3. It is B, 1B. So suppose if it is the ratio, it was a unit ratio bridge, and now if it is the ratio is P there, and this P is greater than 1. That means the arm ratio is 2, 3, 4, or like this there. So what will happen? I will not write it, derive it, all the things there, but I just tell you the result that for this case, for bridge arm ratio P, which is greater than 1, I can write it down that E0 by is equal to E into that is Px, please check it, divided by P plus 1 into P plus 1 plus x. Okay? So, what is the E there? What is our findings, our observations there? Mind it, it was 2 plus x or like this. So, what we wanted that x must be very small than t. But p may be, in this case, p may be, say p is equal to 10. So, here it is 11 and even x is more or almost equal to 1. This one is much smaller compared to this one. I will get a more linear characteristics. I will get a more linear characteristics if I use a bridge arm ratio to be higher than 1. But But is there any problem also? Can you tell me? Is there any difficulty in this case?
Sir,
Is
the
there any?
slope
Yes?
is sir, the slope is decreasing.
The
Means
slope will be
it,
decreasing, very correct. Basically, what we call it a sensitivity. So here it is x, and here it is E0 by E here. And this was, if I look at it, that maybe this is x is equal to 1, or sorry, p is equal to 1. That is the unit arm ratio there. But here we will get that the sensitivity will be reducing considerably, but as the sensitivity is reducing, so here it is p is equal to 10. But what will happen? Sensitivity reduced it, but nonlinearity also reduces. But nonlinearity also reduces. So that is a good idea because to use a higher value of bridge arm ratio, because the sensitivity may be reduced. Okay, use another amplifier of higher gain. Anyway, we will have to use it, but the considerable amount of linearity can be recovered. My last question is it okay? So there are very fundamental things are there which can be understood from the these basic problems, etc. You cannot solve all the problems, other problems also you can look at it. But the last question, say suppose, I think that was problem uh, I think that was a problem 5. So here it is a problem 5. I put the question here. Suppose instead of this one, I put a voltage source, I put a current source there. Instead of voltage source, I put a current source. I think the A was given in this way. Anyway, the direction doesn't matter, but as the problem, I am just giving it. Only the voltage magnitude, I mean the positive or negative polarity will change, otherwise it is the same. And here it is equal to E. Compared to the earlier problem, it is E by R, which is obvious. This was R, 2R coming parallel with 2R, and that is R, and this is your current going for it. So can you find out what is the value of E0? Quickly. What is the value of E0? I can put it mod also. The sign are like this, it's not important. Can you find out?
sir, IRX by 4 plus X.
What was it?
Sir, IRX by 4 plus X.
IR divided by
4 plus X into X.
into X, na?
Hmm.
Huh?
Yes, sir.
So I can say instead of IR, I can put it E. This is for current source, and for voltage source it was Ex divided by 2 into 2 plus X. Okay? This is for voltage source, identical. Which one would you prefer? Which one would you prefer? Which one you would like to have it?
The first one.
Fast one. Why?
The x will be more small than 4.
So that's the thing there. Here we can have a larger x, but similarly, but the linearity will be improved. So better linearity with current source. So naturally, same problem, same thing, whatever we have done it in our second year classes or like this. If you look at it more detail that is there, instead of voltage source, if we use a current source and a simple unbalanced Wheatstone bridge with a unity gain, unity arm ratio, we can get a better linearity compared to this one. But definitely it requires some extra overhead. That is, you need to construct and design a current source which will give you a constant current. So, I leave it to you to design a current source. Mind it, both of them are, neither of them are grounded. Huh? So, try to get a, how do you get a constant current source? Or like this and design it and make it. So, these are small tips which are very essential for understanding and going further into depth of this instrumentation devices like this. So, most of the problems I have already solved, and I think CMRR problem you try to do it. For the first problem we will not evaluate, but we will like to see that you solve it and submit it to, as a proof that okay, you have gone through this rigor. Please submit it. We will do it, give you the portal. But what is important, more important, is to understand the basics of it and to appreciate which circuit is better, which circuit is bad, and compare it, and how can you improve the performance. For example, just by changing the voltage source by the current source, we can improve the sensitivity considerably. The linearity considerably. And definitely, what would be the required circuit for the signal conditioning? That also we should think of it. So I close it. If there is any other question, you can ask me. Yes? Any further question? Please try to solve. You may get many problems from Bentley, from that Palasarini, and many other books. Even Franco, there is a book also. You can get it. Try to solve them. And but unless you solve them yourself, you will not get a feel of it. Okay? So is it okay? Any question or any suggestions? If it is not, then we'll discuss on next class about the next topic, that is the dynamic characteristics. Okay. Thank you very much. Bye.